Welcome to PRS 416 at 5 o'clock on Wednesday, just before the party. I'd like to say I'm amazed at how many people have actually shown up at this time of day. So I'm Rudolph Balaz. Those of you who came to my last session, I'm the program manager for Direct3D 9 on Windows Vista. Sam Glassenberg, he's our program manager for Direct3D 10 on Windows Vista, will be taking the second half of this presentation. So when we went and organized this particular presentation, what we decided to do was sort of give a good breadth. And in the first part, I'm going to focus more on existing technologies in what's in D3D 9 today with high-level shaders. And we're actually going to build a high-level shader that will render the Earth, and we'll get into that. And I'll talk a little bit about the technologies and how it works, just to give you some background. It's not going to be like a really deep introduction to D3D. It's just going to be enough so you can probably follow the code samples I'm going to show. I'm actually not going to talk a lot about the math involved. There's a lot of good books on 3D, and since judging from the last presentation, more than half, if not 3/4 of people are very familiar with 3D anyway. And then Sam's going to pick up after that and talk a little bit about pre-computed radiance transfer and do a geometry shader demonstration to do a particle system in D3D 10. So with that, let's get going. Here's the agenda for today. I'm going to do a really quick overview of D3D, and then I'll do a basic demo where we're actually going to build a vertex shader and a pixel shader for an application. Sam's going to talk about some really cool things you can do with D3D, and especially D3D 10 and so on. And so let's move on. Those of you who are new to D3D, where to start? The DirectX SDK is a really good place. There's some basic tutorials in there. There's a whole bunch of samples on high-level shading language, on the effects system, on the pre-computed radio transfer, high dynamic range imagery. And we're constantly actually adding more and more samples. One of the things is that the DirectX SDK very recently went to a 2-month ship cycle, and it's available on MSDN. And we're constantly adding new tools, new samples, new things for you to look at. So I encourage you all to go and look that up. And the place you go is MSDN, Microsoft.com, DirectX SDK. So feel free to start playing with existing technology, because the really cool thing is it just works on Windows Vista. Those things will work quite well. Now, those people who came to the previous session and we talked about all the extensions we did for D3D 9, what I wanted to point out is that the pieces you need to actually do D3D 9 EX development are actually currently in the platform SDK. And so the steps you're going to have to go through to actually use those pieces right now are, first of all, install Windows Vista. You're going to install the platform SDK on top of that. And then you're going to wait a few more weeks and get the DirectX SDK from October and layer that on top of it, because you need the other tools and things like the shader compiler. This was an unfortunate timing incident, but the current SDK actually doesn't install properly because it's something wrong with our installer. Hopefully we'll be able to change this before we actually ship and actually have a much nicer, cleaner way for you to get all the bits that you need for development. But all the headers and libs are currently in the SDK, in the platform SDK, as well as the documentation for the extensions. So with that, let's start talking about Direct3D. As you can tell, I'm one of those people who like to try and understand how things work at a high level and how the pieces all fit together. So I have more of my Lego diagrams. This diagram is simplified in a lot of ways, because one of the things about D3D is, like D3D 9, for example, there's actually a couple of models for programming it. One is the fixed function pipeline, which actually isn't even represented in this diagram. And then the shader model, which is the one I'm actually going to talk about. The reason for that is the fixed function pipeline is really all about programming a large state machine. You set all sorts of bells, knobs, whistles, and then you say go, and it goes and does something. It's actually, in some ways, a little archaic. And really, the underlying hardware in recent times, most of it has actually changed to not have fixed function pipelines. And even when you're using the fixed function model in D3D, you're actually really using a shader underneath because the driver actually generates the shader for you. So because of that, because the hardware is actually becoming more and more programmable, what we're going to do today is we're going to actually look at shaders and see how you would use shaders and why it's actually easier to use shaders than the fixed function model. So if you look at this diagram on my left, your right, I guess, what you really have is a bunch of triangles which make up your model that you're going to be displaying in 3D. These things get passed through this pipeline from left to right. They get processed by the vertex shader, which deals with the individual vertices and either modifies them or passes them through. The pixel shader then gets run on every single pixel, and something gets put out on the screen. There's also a bunch of extraneous stuff that get pulled into this pipeline, things like the textures that actually get wrapped onto these triangles that are being displayed, as well as constants, things like your transform matrix, things like projections and so on, or maybe some other constant that you happen to use in your calculations. These may get pulled in. And then the last piece, which is the annotation framework, is actually a way for a hosting application to expose its variables to the shader and the effect system so that you can actually link the two together. So that's sort of what we'll be doing today in the first part of this demonstration. So with that, let's talk a little bit about a vertex shader. A vertex shader is really a program that takes a bunch of input. The first one being a stream of vertices that make up your model. It takes some constant, it takes some texture data. And the only thing it's really required to do is to transform that data that it's getting in from its three-dimensional space into the 2D projection on your screen. So what I have there on the left-hand side is your 2D grid of your screen and the 3 points of a triangle. So the vertex shader actually gets run for each one of those points. Now, it also may output some optional information as well, such as the color of the vertice, what point in the texture actually corresponds to that vertex as well. It may, normal data, so the little arrows I have coming off of the triangle, it may output that information. It's not necessary if you don't need it, but it's for some of the effects we're going to be doing later on in this demo, we're going to be doing that. And the only restrictions, obviously, with vertex shader is you can't actually create new vertices, and you can't store results into memory. But since it runs on every single vertex, there's a lot of things you can actually do. Now, let's say we've run our vertex shader on a bunch of this data, like let's say one triangle. And we've mapped that triangle from some three-dimensional space back down onto your screen. Well, once that's done, some magic happens. And those 3 points are actually interpolated for every single pixel on the screen. And for every single pixel on the screen, your pixel shader runs. And that pixel shader gets this interpolated data that's being passed down to it. So as you can see, I have the original 3 vertices on there, and now the pixel shader on every one of those dots runs, and it gets a chance to set the color for that point. So that's the required output from your pixel shader, is that color. Again, it can get all sorts of other information too. It can get texture data if it needs to wrap it. It can get constants. It can do a bunch of other stuff like that. Or in the newer models now, you can actually even write to multiple surfaces, right? So you may actually be writing to the screen, but some of the more advanced techniques, you may be doing multi-pass rendering where you actually write to multiple outputs that actually aren't on the screen. Then you do something like composition, put it all together, and then render that as a final pass. Or you may be doing some effect like glass or something where you have to pass through it several times. And again, the only restriction on the pixel shader is you can't read and write the same texture at the same time, because the interesting thing about the hardware is that they have multiple of these texture units all in parallel. They're all running the same program. They're operating on different pixels on the screen. So while you're actually thinking about this as, okay, I'm writing a program that works on one single pixel, what's really happening is the hardware is running that same program on a whole bunch of pixels at the same time, and that's how they get their speed performance. And so what we're going to do today is we're going to write a high-level shader language. A high-level shader language looks a lot like C. The syntax is very similar. It has, the same feel and look. And I'm going to be using actually Visual Studio to modify my sample. You could be using Notepad or whatnot. It's just a text file in this case, and it gets compiled. And what I have here is a vertex shader. This is pretty well a minimal sort of vertex shader. It gets some input. It calculates the position in 2D space by multiplying it by the world coordinates, the view, and the projection. It gives you a new transform position. It does some this particular one does some calculations on the lighting that each vertex may have. And again, as soon as you calculate something about a vertex, that information can be interpolated for the pixel shader. So if you want to do very basic, shading where you start at green at one vertex, blue at another, and red at another, you can actually have it shaded by just by letting the system interpolate for you. So we'll be showing some of the stuff very shortly. So with that, let's get to the demo. The demo that I'm going to show is actually an 8-part one. What I'm going to do is actually take a very simple vertex shader, and we're going to add line by line. First, we're going to do some diffuse lighting on it so that it actually has some field, make it look like it's a 3D object. We're going to then texture it to make it look like this Earth here that I have on the screen. We're going to blend a number of textures together. We're going to animate it. And the interesting thing about the animation is I'm going to do the animation on the GPU in the shader as well. So it's actually not going to be the CPU doing the animation. It's going to be the GPU. And a bunch of other effects. And I'll walk through what each one is as we go along. So with that, I'm going to switch over to my demo machine. Here's the final result. This is what we're going to build. Let me move it so you can see a nice little Earth. Those of you who walked by our booth yesterday probably saw this. It's a globe of the Earth. I have a map of the Earth. I have a night side and a dark side and so on. So let's go and look at our very first Earth. So what I have here is where we would start off with. And this is a sphere, but it looks pretty flat. And here's the shader program that we're using. This is actually an FX file because we're actually hosting this inside the DX viewer. But there's a bunch of information here. There's some global variables such as the world matrix, the view matrix, and projection matrix. These things are information that I'm actually getting from the host application. And that's what the SAS bindings are letting me declare on how I'm getting those. Some information I have to declare when I'm writing a shader, things like the vertex shader inputs. For this sample, I just need one thing, the position of the vertex in 3D for that piece of geometry. And the output, which in this case is going to be the transformed position in 2D space. And then let's look at the vertex shader. What does the vertex shader do here? It gets the input. It does that multiply where we take our input position, multiply it by the world view and projection matrices, and put it as output. It's a very simple shader, doesn't do much. And the pixel shader actually does even less than that. It gets the output from the vertex shader interpolated, as I talked about, for every single pixel on the screen. And what we're doing right now in this vertex shader or pixel shader is just setting the color to, what was it, blue? Yeah, blue. So what I could do is I could just change the color. And when I switch black, it's now pink, right? Again, it's flat shaded because I have no idea of where the light's coming from or what the shape of the object is. It's just flat. So let's move on and do something more interesting. So I'm going to open up my diffuse model. And so for diffuse, I've added in the direction of light. Again, this is in the application I've created. There's a light. It has a direction. It has a position in space. And so all I'm doing is binding this variable to that so I can use this calculation in my shader. Nothing much more has changed. I've added an input, which is the normal. So at every vertex, I have a normal vector that's pointing away from the surface. The data that actually makes up that sphere was created with that information already built into it. So I'm just asking for that information. And so I'm going to do some calculations on it in the vertex shader. I'm going to pass it down to the pixel shader. So vertex shader change. But the only thing I'm going to do is I'm going to take that input normal and transform it into world space so that when I pass it down, it goes down to the correct format to the pixel shader. So far, pretty simple transform. In the pixel shader itself, I've done a couple of things. One is I just want to make sure that this value of the normal vector is between 0 and 1. I don't want it to be either negative or too big, so I normalize it. You may actually not need to do this depending on how the math works out. And right now, we're, again, setting the color. As you can see, it's still purple. So I'm going to uncomment a couple of lines. And what we're going to do is we're going to do a very simple lighting model that's dependent on the angle between the direction of light and the angle of the normal. So what we're actually going to do is calculate that angle and use that as a ratio for how much we're going to light that particular vertex. So if it's bang on, they're both parallel, we want that to be maximum brightness. If they're actually in opposite directions, we want the surface to be black. And by doing that, I'm going to do that using the dot product. I take the direction of the light. Actually, I invert it, and I multiply it by the normal. And I saturate it, again, so it's between 0 and 1. And then what I do is I multiply that light value by the color of the light, which is also a constant that I have available to me. And some fudge factor to make it look nice in terms of what I want. And let's save that file, and that's what we get. Right? And as you can see, it's shaded, and we get a nice little sort of 3D effect. So far, so good. So now that we actually have some lighting happening, let's also texture this, right? Because we want it to look like the Earth. So I'm going to start with the next one, which is the texturing. And again, all I'm doing each time is I'm adding just very simple things to the program. And in this case, I'm going to add a texture. So the texture I have is this thing, this diffuse texture, which I'll just open up to show you what it looks like. And, oops, too far. That looks like basically a map of the Earth, and texture is a two-dimensional texture, and we're just going to wrap that around the sphere. And so to do that, first of all, we have to declare the texture in our effects file so that we can actually import it. And for every single texture you have, you need to have a sampler that tells the system how you're actually going to sample the point on the texture that you're going to use. And in this case, we're using an isotropic filter. Changes in our declaration for the inputs, we now need a texture coordinate. Now, the texture coordinates are actually associated with the vertices in the model, and that defines where on the texture this particular vertex exists. So when we actually built that sphere, we defined how it mapped to that two-dimensional texture of the Earth. And then we're also going to output that from the vertex shader. So now if we look, not much else has changed. We're still doing the normal calculation. And all we really do with the input texture coordinate that we've actually have on our model is just pass it through and pass it down to the pixel shader. We don't do any calculation at this point. The actual real heavy lifting is going to happen in the pixel shader, where we actually blend the texture with the light calculation. So let's look at that. So everything else that I'm not pointing out is the same from the previous file. So that, and these files are arranged in this way, so you should be able to look at them afterwards and actually walk through them yourself. What we're actually going to use is this instruction called Direct3D, which lets me use a sampler and sample a texture at a particular position. Now, the input text coordinate that we passed through in our vertex shader has now been interpolated for us, so it's now somewhere on that triangle on that map of the Earth. So right now what we have is the original picture, right, or original image. So when I uncomment this, what will happen is this Direct3D instruction will go to that texture, sample at that point that corresponds to that location on that texture that maps to this point on the sphere. And we're going to modulate the color that we currently have, which is this white color, with this color in the diffuse map. And so when I save the file, we have a nice little Earth. And you notice that only the bright side is lit, because the dark side, the values are either 0 or negative, which means nothing's going to show up on the screen. Right? Negative colors are black. So now I'd really like to have both a day and a night side. So let's move on and do that. And what we're going to do that is we're going to do that with texture blending. We're going to have the same day side texture, and we're going to now add on a night side texture for the night side. And I'll just show you that file quickly. And again, it's the same thing as before. It's a picture of the Earth. It doesn't show up as well on the screen here, unfortunately, because all you see is the cities and the lights. But on the actual laptop, and if you want to come to the lounge tomorrow, I'll be in the lounge tomorrow. I can actually show you this in a little clearer. You can actually see the land masses and everything else like that. I'll try and boost up some of the constants in the file so that these show up better. But what we're going to do is we're going to take that texture, and all we did again is we added now a new texture declaration, a new sampler for the night sampler. Nothing else has changed in terms of the inputs, outputs. The vertex shader hasn't changed in this particular place. The place again that changes is here in the pixel shader. And what we're going to do is we're going to calculate how much of which texture we're going to show. So if we're fully in sunlight, we want to show the light texture. If we're fully in darkness, we want to do the dark one. If we're somewhere in between, we're going to blend the two colors together based on some ratio. And we're going to do that using this sunlight ratio. And the actual value I'm going to use is 2 times the current light value that I've calculated. And I'm going to saturate that value so it's between 0 and 1. I'm going to sample the night texture as same as I sampled the day texture using the 2D texture command, or the text2D command. And what I'm going to use is this other intrinsic built into HLSL called lerp, which is a linear interpolation between the night color, the day color, based on what the sunlit texture is. So when I do that, I'll save that file, and let's see if that shows up. There we go. You can see that I have a nighttime and a daytime. And again, because the light isn't quite bright enough, let's see if I can just... Yeah. Let's just see what happens if I double this. I haven't tried this previously. I made the Earth a little brighter. And you can see that it's a little brighter. You can sort of see the line. Again, it shows up better on the LCD screen. The projector, for some reason, isn't as bright. All right. Well, that was good. Now let's do the next thing. We've now blended. We've created an Earth that looks sort of realistic as day and night side. The other thing we want to do is animate it. And I'm going to do this again on the GPU because I don't want to waste the CPU's time in animating this. I want to have the GPU, since it's doing nothing, it's calculating these vertices anyway. So the vertex shader is actually a really good place for me to do these calculations. Not only do I transform it from 3D space to 2D space, but I can actually transform it into a rotated space and then transform it into its clipped space. So I'm going to do that by grabbing another piece of data from the application, which is the current time. I'm going to use that as my key for my animation. Nothing changes in the textures that I've used. I'm adding a helper function that takes an angle and returns to me a rotation matrix so that I can just multiply it by it. Nothing's changed in my input-output definition. And in the vertex shader, what I'm going to do is my world coordinate I'm actually going to modify. So at every 10 radians or whatever it is, or 10 seconds, I'm going to actually change the world coordinates by rotating it a little bit. So I take the world coordinate, multiply it by this rotation matrix, and I don't have to change the pixel shader at all, and all of a sudden my world starts rotating. And you'll see that eventually I'll get a night side coming up. It's rotating the wrong way. Yes, it's rotating the wrong way. And as my demo instructor has always told me I'm not going to deviate from the script that far because I'm sure I'm going to make a mistake. All right. So we have it rotating the wrong way. It's just a minus sign. I'm not that brave today. Okay, so let's move on to the next one. Now that's a nice realistic Earth, but I want to make it surrealistic. So in this particular application, what I'm going to do is add an environment map. For those of you in previous session, you saw me talk about environment maps and cube maps and so on. So what we're going to do is we're going to take a map of one of the building lobbies at Microsoft, and we're going to actually add it in. And so what I do is I just take a cube, another texture, an environment map, add that in. And I'm going to actually be passing a couple of new things down to the output. So I'm going to take normal coming in, a tangent coordinate. Again, this is data associated with the vertices in my model that have been pre-computed for me. I'm going to take those, do some calculations, and pass them back, as well as an I vector, because I want to know where I am relative to the light, relative to the normal. I'm going to use those to do some calculations so that I can figure out how much reflectivity I'm going to have on the surface. So the I vector I calculate based on really the position in the world minus the camera, which is the thing that application actually knows about, and that will give me a vector that I'm using for my calculations. Other than that, I believe everything has stayed relatively similar. In the pixel shader, again, because I've put that as output from the vertex shader, again, it's been interpolated for me, and I just need to make sure that it's properly normalized. And to do the environment mapping, what we use is this, I'm going to do this here where I calculate the reflection angle using this nice little intrinsic that's made for me called reflect. I'm going to take the I vector, I'm going to reflect it into normal, which gives me back a reflection vector. I'm going to calculate a reflection ratio, and the ratio I'm going to do based off of another map, which is a mask. All that mask has on it is the water of the Earth. And it has values for the water because only the water is going to be reflective. So I'm going to use that by sampling that texture to give me back a value that I'm then going to modulate the environment map where I do a cube lookup of the reflection vector. I multiply it by the ratio based on this other texture that has the water in it. And then put in a little fudge factor. And when I actually do that, I get a little Earth which reflects. And because the mask only has the water in it, the land doesn't reflect anything. So that's gives me a nice little effect. All right. So let's move on to the next one. In the next one, what we're going to do is actually add a specular highlight. Now that it's a highly reflective object and it's reflecting the environment, right? The one thing your eye tells you is wrong here, this light here, right? Because I have a dark side and a night side, and I have this reflection in it, but there's no highlight, right? There should be a really bright specular highlight somewhere on this surface. So what we're going to do is add in a specular highlight. We're going to add the specular highlight in the pixel shader. Again, nothing changes in the vertex shader for this sample. But what we do is add a specular highlight. And the specular highlight is calculated, again, by taking the reflection vector. We calculate that angle with the direction of the light. And we saturate. That gives us our specular value. And in this case, I'm just using the ratio of the reflection, the direction of the light, and I'm raising the specular to some power that determines how big the area I'm going to highlight. And I add that as a highlight to the color. The reason I'm adding it rather than modulating this time is I want it to saturate it to white. And let's take a look. And you can see there's my little highlight. That shows me where my light is out here. Actually, for those of you who are interested in debugging these sort of things, one of the things I could do is, rather than passing all that other information back to, because when I was first developing and working on this, I wasn't giving me the right answer. I was wondering what was going on. So one of the things I did was I just used the highlight itself as the value I'm going to texture that cube with as the color. And so what I can actually do for debugging purposes is I can actually see that color being represented for every single pixel, and it'll sort of let me trace down where my issues and problems were. So at any point you can actually do that. Just pass out some three vector value and use it as a color. All right, so that was specular. Now let's move on and do normal mapping. Now the thing about this globe is that it's nice, we've textured it, but it could have some more detail actually associated with it. And what I'm going to do is I'm going to take a normal map, and I'll just show you this normal map. And what we're going to do with that normal map is we're going to use that information to provide higher level of detail on the surface. We're calculating the value of the light and the color at every single point anyway. I can now do an extra texture lookup, look up on another bitmap the normal that it should be, modulate that with my other calculations to actually make it appear like the surface had more triangles on it than it really does. So I can actually save geometry processing, save vertex processing, and do all my do this little extra calculation and make the image look so much better, make it look like it had, you know, some height, some depth, some, you know, more detail than it really actually does have. So I'm going to close this, and again, we do that in the normal map case. What we'll do is add a new texture, this normal map texture that I just showed you, and again, with every texture we add a sampler. Not much else has changed in this part. But the big difference is that, again, the normal map is stored in what's called tangent space, which is relative to the actual texture itself. So one of the things we're going to have to do in the vertex shader is actually multiply them by the world coordinates to get them into the right coordinate system for the pixel shader so that they're interpolated correctly. So I do that here and pass them down. In the pixel shader, there's a couple of things I'm going to do. One is I'm going to do a lookup on that normal. I'm going to do a little fudge factor to make sure the result is unbiased. And then I'm going to transform, or first of all, create the tangent frame and transform that normal by that tangent frame. And so what I'm doing here is sort of taking that normal vector, moving it into the space that the object is, so I have a new angle that I can use in my lighting calculation. And then further down, I use that. Where does it go? Oh, actually, it's part of the normal. So the normal value gets used later on in the normal calculation to calculate the light value. So if I go back here, and actually, you can't really see it as well on this projector. So let me do something to bring it up. What I'm going to do is, rather than displaying all that other texturing stuff too, I am just going to return only the normal map information as part of the color so that you can actually see it on this monitor. What you can see is the mapping as it gets wrapped on. So what it's done is it made those areas look raised. And so I've actually added that. It made it look like there's more triangles. So I could have actually done this by adding more triangles to the sphere, but it was simpler just to use a texture. And again, it's more obvious on a different monitor, so come by tomorrow and I'll show it to you. That's what it looks like. And then the last thing I'm going to show, hopefully I haven't run out of time, is this is an Earth. It has atmosphere, right? I really want it to glow a little bit around the edges, right? Because as light passes through more atmosphere, it should be bluer, right? Well, I'm going to use the same thing I used for the specular, right? With specular, I used the formula to make a highlight at one spot. Well, I'm going to take the opposite of that. So rather than highlighting the spot under the specular, I'm going to highlight the edges. So what I do is in my atmosphere, I just add one thing, and I only add it to the pixel shader at the end. What I do is I do a calculation on the atmosphere for the atmosphere value, which is the I vector and the normal. It's the same calculation I did before for the specular, except now I've subtracted from 1 because I want the opposite value. And I use that to modulate the atmosphere value. And I add that to the color so that what I should get, if I don't make a typo, is get a bright blue band around the outside of the sphere. Let's see how it looks. As you can see, it's a brighter blue around the outside. Actually, let's even do this. Let's just look at the atmosphere without. You can see the blue band. And by adjusting that formula, I can make that band bigger or smaller and do things like that. So that is my demo so far. And let me switch back to the presentation. That should give you an idea of how you would go about building a high-level shader language, vertex shader, pixel shader. Those are the two pieces of technology that are in D3D9. I'm going to hand it over to Sam, who's going to now talk about some other cool things you can do with D3 as well as future D3D10. Thank you very much.
Hello, everyone. I'm Sam Glassenberg, Program Manager for Direct3D 10. I'm also responsible for D3DX, which is a library that encompasses a slew of 3D application development tools, like some of the stuff that Rudy illustrated, HLSL, the effects system, and as well as some additional tech to do things like pre-computed radiance transfer and spherical harmonics. Which is where I'm going to begin today. Has anyone here used pre-computed radiance transfer and spherical harmonics? All right. So I guess if you thought the highlight of your day was going to be going to Universal Studios, I guess you probably didn't expect that you'd walk away from here understanding spherical harmonics and PRT, but you will. I'm going to begin where Rudy left off, that basically was this notion of local illumination. So all the techniques that Rudy presented illustrate local illumination. The idea is light hits the object from some distance away and goes directly to your eye, bouncing off a normal or something like that, maybe grabbing a reflection map, but bouncing straight to your eye without interacting at all with the rest of the scene. And this creates, a cool effect, but it is, somewhat plasticky and artificial looking. You recall that Rudy's calculations only took the normal and the light position into account. It doesn't take into account the geometry of the rest of the scene. And this is the type of lighting that we've come to expect from most applications and game titles that evaluate that evaluate point lights directly in the pixel shader. But if we really want to create realistic-looking objects with a sense of presence in the scene, we need to model global illumination as well. This is something they've been doing for a long time in feature film and movies like Shrek 2 and the like. Been doing this for probably over a decade. The reality is that light doesn't just hit every point on the object and go straight to your eye. It bounces around the scene. In this example here, light can be occluded by geometry, creating shadows and dark areas and crevices. Here you see the visual difference just from adding shadows alone. It looks a lot more compelling and realistic. Detailed shadows and crevices, add a whole new sense of richness. And when you're working in 3D, shadows are really vital. It's a vital visual cue in order to understand where your objects are relative to the rest of the world. Light also bounces around the scene. Most of the light, you see, day to day in indoor environments doesn't come directly from light bulbs, but it's bouncing off the walls and other objects in the scene. Yes, in this room, I think they're all pretty much coming from those two, but I can't tell if they're coming from anywhere else. But you can think about when you have, what happens if you have a bright white light in a completely red room? All the objects in that room are going to turn bright red. But if you're using a local lighting model, you would check what's my material, what's my light color, and you'd lose the contribution that the rest of the scene provides. So you can imagine a lava cave, a museum, or walking through a brightly lit, thick forest. Colors are going to be absorbed, colors are going to bounce around, and it's these effects that give objects a feeling of presence in the scene. And in materials like human skin, marble, and wax, not only does light bounce around on the surface, but light will actually come into the material, bounce around, and then it can exit at a completely different location. And it's this kind of soft, complex, translucent look that we look for in human skin, and that's one of the reasons why our visual system is so good at sort of trivially detecting a fake. When they try to create artificial human beings, it's like if they don't have really good subsurface scattering and realistic-looking skin, it all just looks like plastic. And you can observe this behavior in the extreme by taking a flashlight and putting it up to your hand, and you can see all the light, scattering through. With local illumination only, if you want to, you can't, if you're going to try to render organic materials like, wax, leaves, goo, slime, milk, paints, blood, all things that are very important for video games, you're going to need, if you don't use subsurface scattering, you're just going to render it like opaque plastic. And that's just totally, it's a totally crude approximation for how that material would actually behave. One approach to global illumination is just bake things like shadows and inner reflections into a texture called a light map. And then you just map this onto your object. And indeed, 3D actually provides some additional functionality to help you do this. But this only works if your lighting environment is going to be totally rigid. In the real world, the lighting environment is always changing. It's not always 3 o'clock in the afternoon in Maui. You're going to have, cars are going to drive around with headlights, soldiers on Mars are going to carry flashlights, and your street lights are going to flicker, and so forth. And in film, you don't have to, you can spend 6 to 8 hours per frame, as your lighting environment changes, bouncing a million photons through your scene and, generating a completely new compelling image. But in a real-time application, you need to render that at 60 frames per second. And that's where PRT, where pre-computed radiance transfer comes in. PRT gives you realistic global illumination in real time with dynamic lighting. So here I have, basically, this is the PRT demo that ships with our SDK. You can download it, play around with it. This is basically, well, this isn't illustrating PRT. This is illustrating diffuse lighting that Rudy introduced a few minutes ago. What I can do is run the PRT simulator on that content, and I'll say, OK, I want to enable subsurface scattering. And we'll let this thing go. So what's happening right now, as these numbers increase? Basically, what's happening is the PRT simulator that ships in D3DX is shooting thousands of rays through the scene, bouncing them around, and figuring out exactly how the scene responds to any lighting environment. So if I switch to PRT, now it was basically simulating a sort of a waxy material. Now if I move my light around, I get this soft shadow of the sphere casting onto the surface. And if I take my, let's say I'm looking at it from this angle, and I use N.L lighting, and I move my light right behind that back panel, I don't see anything. But if I use PRT, well, it bleeds right through. So you get this really realistic effect that works for any arbitrary lighting environment. I can move my light around. In fact, I can use a really complicated, I don't even have to use a point light. I can use any arbitrary lighting environment that can be represented in a texture where we have, like a bright, like a eucalyptus grove where you have a bright sky and a dark ground. And my object is going to respond correctly. So basically what the PRT simulator has done is it's figured out for any point in this complex scene, what is its radiance at the end? What is the, after the light bounces around the scene, what is the exit radiance at every single point on that object? What is that, for any arbitrary lighting environment, for any lighting configuration, at a given point, what is that point going to actually look like? Is it going to be bright? Is it going to be in shadow? Will it be lit directly? Is light going to shine through from the other side of material and light that individual point? And what the PRT simulator does is at every point it computes a function that maps any arbitrary lighting environment to the outgoing radiance at that point. So to give you kind of an example of how this gets constructed, let's take a look at some configuration. Here we have a point on a surface. We have a point on the surface. We've got these two occluders up top and to the right that aren't going to let any light through. We've got a reflective green object to the left that is going to block light, but it'll reflect it. And then we have some translucent material on the bottom. What we want to understand is, given any arbitrary lighting environment, what's the response of that point going to be? So first we'll look at direct lighting. And if you look at direct lighting first, you're going to see that only light coming in from these directions is going to brighten the point, because anything coming from these other directions is going to get blocked. And as a result, we're going to get this little function. This function represents how light coming in from a given direction on the sphere contributes to outgoing radiance at that point. So the larger the radius in a specific direction, the more incoming light from that direction is going to brighten the point, which is why more light coming in from this direction and light coming in from this direction are going to brighten it. The light coming in from the top or from the left is going to get blocked and isn't going to have any contribution. Now let's consider that we have a translucent material on the bottom. So that means that some light coming in from below is going to contribute to that point and brighten that point, and that's going to create a little lobe on the bottom of that function, which basically says, okay, light coming in from the directions below the point is going to have a contribution, but it's just a little bit because a lot of that light isn't going to make it through. Then if we consider that the material on the left is reflective, light coming in from the upper right side is going to come in, bounce off that object, and then it's going to hit the point, which is going to mean that light coming in from the upper right is going to have an even bigger response, and that's where we get this this larger, that's going to increase the size of the upper right lobe just a little bit. So in the end, we end up with this, weird, cool, blobby, spherical function at every vertex on our entire object. And this is going to represent our point's response to any arbitrary lighting environment. Let me switch back. So I'll just show you a quick demo scene that's going to actually illustrate what this transfer vector looks like. Just takes a second to load. So let me turn off light probe. Here we go. So here we have this lighting environment. And what I'm going to do is, I can click the D key, and at any point, I can actually view this radiance transfer vector. So if we look at this point in the middle of the surface, well, no matter where my light comes from, it's pretty much going to be the same brightness. But if we look at a point, let's say, in between these two pillars, we're going to get a more interesting function. And what that's basically telling us is if light's coming in from the right, well, then it's going to brighten that point. If light comes in from the left, it's going to brighten that point, or the top. But if light comes in from behind the pillar, that point is going to be in shadow because the radius in this direction is smaller. As you can see, that point is in shadow. We can see an even better example on the back wall. There we go. Where you see that, if a light comes in from this side, directly through the pillar, it's going to get blocked, and there's basically zero radius. It's going to be in shadow. But if it comes in from the left or comes in from the right, that point is going to be lit brightly. We can also see what subsurface scattering looks like. Here we have this object that has a pretty even diffuse response. You see pretty much a spherical function. If we look in darker areas like the eyes and the mouth, the radius is going to be smaller just because these areas are usually a little bit darker, because light coming in from any direction is going to be shadowed out. But the interesting place is if we look in the ears. So you see these ears are going to actually bleed a little bit of light through. If I look at the radiance transfer function on the ear itself, I see I get these two lobes, which tell me that light coming in from both the front and the back are going to create a response. So we have that complex spherical function on the sphere. How do we actually store it so we can render it efficiently in real time? We could just store a texture at every vertex that represents that spherical function, maybe in a cube map or something, but that's going to be prohibitively expensive. That's going to be a ton of memory. So in order to actually store this spherical function, we're going to look back to linear algebra. And if you remember, any n-dimensional vector in linear algebra can be represented by a combination of n independent basis vectors. So a 2D vector can be represented as a combination of x and y components. And likewise, the same concept applies to an audio signal. You can represent any 1D signal as an infinite combination of sine waves at various frequencies and phases. So in the end, all you're doing is constructing a vector. You're representing that 1D signal is just a bunch of values. It's just a vector. And the more elements in your vector, the more accurate your representation is going to be. So with our spherical function, we can take it and represent it with another basis, the spherical harmonic basis. And any spherical function can be represented as a combination of these independent spherical harmonic bases. You can just express it. The blue is negative, the red is positive. You just mush a bunch of these together, and you can get any function that you want. The more bands you use, the more accurate representation will be. So now this actually gets interesting because so we can take this and we can represent it just as a combination of these little lobes, and we can, so in the end, this function just breaks down to a bunch of numbers, just a vector. And we can do the same thing with our lighting environment. We can represent our entire incoming lighting environment with another spherical harmonic vector. So here we have 3 lights that generate, some sort of spherical function. And the more coefficients we use, the closer our approximation to the surrounding environment. So we have a vector that describes our lighting environment, and we have a vector that describes the response of any point to any lighting environment. In order to actually compute the result, it's just a dot product, which GPUs can handle ridiculously fast. So in the end, this is amazingly cheap. For any arbitrary lighting environment, any number of lights, or any complex lighting environment like the one you see here, it's just a dot product at every point in order to figure out what the response is. And to kind of illustrate this, let's say we have a point on this surface. And here, we've got an occluder up and below, so we're going to get this type of transfer function. If I bring in a light on the upper right, we'll get a lobe that looks kind of like this, and we'll have overlap. When we do the dot product, we'll get a response. It'll be a bright point. If we bring in 2 lights above and below, they're going to create a lighting environment that looks like this. And we do the dot product, there's no overlap, so it's going to be dark, because though these objects are going to occlude both of these lights. But if we say that the surface below is translucent, then we're going to have a little lobe here. So when we actually do our dot product, we're going to get a response because there's a little bit of overlap, and it's a slightly brighter than it was before. So, oh, we're not done. So now that we've gone over some cool techniques that you can use to get your feet wet with D3D, in the last few minutes I want to talk a little bit about what's coming in Windows Vista. You remember back in the day, Direct3D 8 basically served as the basis for the Xbox console. And now, indications are we're going to see a new console generation built on Direct3D 9 hardware. And Direct3D 10 is the next step. Rudy's already introduced it. It's a major re-architecture, rebuilt from the ground up in hardware and software to deliver an unprecedented visual experience. And our roadmap has D3D 10 serving as the basis for the next few releases of D3D. And if history serves us well, we're going to find that D3D 10 and subsequent versions are going to serve as the basis for the next generation of consoles. But the latest and greatest Direct3D debuts on Windows, and Windows Vista is no exception. The major steps in Windows core graphics innovation, I guess, could be categorized in three categories. The first step is evolving the GPU from a device dedicated to one full-screen exclusive application, such as a video game, to a resource that's efficiently shareable by everybody in a stable way. And this is what the Vista display driver model is all about, as Rudy explained earlier. And Direct3D 10 is built on VDDM, and it takes a huge step forward in the last two, in visual effects capability and GPU robustness. It's all about these last two items on the slide. The way we enable these new visual effects is by increasing GPU capability and programmability. And as a result, we're evolving the GPU into a more general-purpose processor that can use its large array of shader processing cores for all sorts of data parallel applications in both graphics and beyond. So first, we'll talk a bit about rendering. A common theme in D3D 10 is improving what's known as small batch performance. And I can easily spend an hour on that subject alone. Suffice it to say, the key idea here is that you want to reduce CPU overhead in both the runtime and the driver to maximize the variety of content that you can shove onto a frame. So GPUs today can render millions, hundreds of millions of triangles in a second, but where their bottleneck we find is on the CPU side, because every time you want to switch a material, you want to switch a shader, you want to issue a new draw call, you have to pay some tax for it. And D3D 10, by design, vastly increases the number of unique materials and objects that you can push onto a frame. I don't have time to go into all these effects in detail. We can talk about it if you want to stop by on Friday in the presentation lounge. But suffice it to say that in D3D 10, the GPU can do a lot more than just render pixels. It's a fully capable multi-pass geometry processing machine that can bind resources ubiquitously throughout the pipeline for both input and output. You've seen this about an hour ago. D3D 10 provides a single guaranteed feature set for developers to target all the features that are required. And we've worked very closely with the hardware vendors to remove as much unnecessary hardware variation as possible. So you can really leverage this as a reliable coprocessor. We're providing a near IEEE compliant, reliable coprocessor that's comprised of common shader cores for you to leverage in your data parallel applications. And I'll illustrate a quick example of how you can leverage this in a minute. As you've heard already, the whole pipeline has been completely revamped with new shader stages that enable a new class of effects and applications. And the Direct3D runtime is in place. You'll see it first in Vista Beta 2. But as Rudy mentioned, the hardware for D3D 10 isn't available yet. So everything that I'm going to demo to you guys live today is going to be extremely simple because it's running in the reference rasterizer, which emulates a complete D3D 10 GPU running in software on the CPU. And even though we don't have hardware, I still wanted to give you guys a taste of what developing on D3D 10 is going to look like. So here's just a quick example of a particle system running completely on a D3D 10 GPU. What I want to convey is how easy it is to map your application on a D3D 10 constructs. This is running several orders of magnitude slower than dedicated hardware, but it at least shows you what the programming model is capable of. When you actually map your application to D3D 10 constructs, you can consider how to, how you'll be able to basically leverage 32, 64, 128-bit shader core processors running in parallel on the GPU without actually having to think about it. So, why are particle systems specifically interesting? Right now in a game, if you want to do an interesting particle system for explosions or smoke or volumetric effects, you're going to have to, if you're going to want to create and destroy particles dynamically, you're going to have to do all that work on the CPU because, as Rudy described earlier, the vertex shader has a one vertex in, one vertex out policy. You can't amplify or de-amplify geometry. And you also can't stream the result out directly to memory in D3D9. So in D3D9, if you want better AI or gameplay in your game, that means you're going to have to reduce the number of particles. But in D3D10, you can do all of this work on the GPU, and you can have orders of magnitude more particles for a more compelling effect. So all the code we're going to write today for D3D10 is using the new effects system, using HLSL. As Rudy described earlier, the effects system is a material and state management system for the GPU. And using effects, we can treat our entire particle system like content, which an artist or a technical director can tweak without having to recompile the app. And then the effects system handles sending all this stuff down to the metal for you and running it on the hardware. So the end result that we're generating here is graphical, but the point is it really doesn't have to be. The majority of the work that we're doing here is pure data processing that we're reading back in a subsequent pass to actually render it. But you could just as easily read back this data on the CPU and use it for another purpose instead of rendering it as particles to the screen. We're doing all of our work on a single buffer. It's basically just a dynamic array of particles that we're going to feed through the GPU in ping pong. We're going to store a type, for we saw different colors. We've got a launcher, a shell, different types of embers. For every particle, we store a position, a velocity, and a lifetime. Let me switch over to the Vista machine. So here we basically see a data structure which basically describes exactly what we're going to be reading in: a float 3 position, velocity, a float timer, and a integer type. And we have some other data structures that we're going to use to pass data in between the various stages of the GPU. And we're going to feed these values into the geometry shader as individual vectors or points, and then we're just going to emit an array for each invocation. So the majority of the time, we're just going to take one value in, one value out. But sometimes, if a particle is going to die off, we're not going to emit anything. And if we're going to want to emit a whole bunch of particles, if we're going to explode a shell, we're going to emit a whole bunch of particles. And then after that, we're going to use stream output to take the result of the geometry shader and write it out to memory. And this isn't. It could be data, or it could be a mesh, or or just an anonymous stream of whatever values you want. And since we're amplifying and de-amplifying, the size of the data set is changing. In D3D10, we actually cache the amount of data streamed out in the hardware, so you can actually automatically tell it to just render or just process as much data as was previously generated. And like I said, we can use this for geometry as well. Here's an example of something our samples team put together that basically illustrates sort of dynamically generating vines that grow and die off. And this is done completely in hardware. There's no CPU intervention at all for a kind of haunted house effect. So basically, our particle system is going to operate in two passes. The first stage, the geometry shader is going to update the particle's data. Just Euler's method. It's going to compute a new position and velocity, and then it's going to decide whether to amplify it or de-amplify it. So in this case, we might explode it into 3 new particles. And then the result is going to be streamed out. And here below, we've actually defined what the format is of the data that we're going to stream out to our buffer. So this is basically our technique in the effect system where we're setting our vertex shader that's just passing the data through. The geometry shader is going to go through and it's going to advance the particles and then stream out the data to the buffer. And then we're not going to render anything, so we're setting our pixel shader to null. In the second pass, we're going to pull the data from the buffer and we're going to render it. So the geometry shader is going to take that position value, which is just a point, and it's going to amplify it, emitting 4 new vertices. And this is going to generate a point sprite. These triangles are then going to be rasterized into pixels to actually render the texture in the appropriate color. And then since the firework embers are basically emitting pure light, we're going to use additive blending to combine them together in the frame buffer. And that's where we basically say, OK, set blend state in this technique to use additive blending. And then here we're just using both a vertex shader, geometry shader, and a pixel shader to render our result in the second pass. So here we go. This is running in the reference rasterizer. This isn't a video anymore. This is running live. Go, ref, go. Watch those little particles chug along. So right now I've got this set up so it's basically just emitting particles at some rate, and it's not doing any geometry amplification at all. So here I'm just going to kind of walk you through what's going on. We've got our textures and samplers, just like Rudy showed earlier, where we're going to load our particle texture, and we have a little texture for random values to make our particle system look random. We've got a bunch of state objects that describe the configuration the GPU needs to be in order to do additive blending or to do no blending at all if we're just doing our first pass. We have these constants that Rudy described earlier. Now in D3D10, constant data is actually organized into things called constant buffers. So you'll recall what we want to do is minimize the amount of CPU overhead in order to actually issue our shader calls. So what we want to do in D3D10 is you can organize your shaders by frequency of update and use into these resources called constant buffers. So what actually happens is the shaders themselves can share these constant buffers, but when you're actually doing updates or sets from the CPU, you're only setting the stuff that needs to change at the current time. So you can organize your data appropriately, so for any given shader, you're only updating the minimal amount of data. Got our pound defines, some pass-through shaders. This is our generic handler, which we're basically calling in all cases to go through and update the position, update the timer for every particle, and update the velocity based on just basically accelerating it, adding gravity, and then emitting the just outputting the particle as a pass-through. So now I'm going to go to the particle handler for the shell, and I'm going to say, okay, don't use the generic handler. Instead, we're going to use this other hunk of code, which is basically just 2 for loops. We're going to iterate through once, and we're going to emit a bunch of ember ones. These are guys that just go off and die. And then we're also going to we're going to output 10 of those, and then we're going to output some random number of ember 2s. So now that I've activated this code, I can save it, and since an effect file is just content, I can update my result, and then so without having to recompile my app, now it's automatically it's going through and using the new D3D10 emit intrinsic to emit a whole slew of new particles. So right now it's just about 6 o'clock. I guess I'm going to let if you have any more questions or want to see more examples of the source code, you can show up to the lounge. I guess D3D10, the best day is probably to be there on Friday. All the samples and demos you've seen here, plus a whole bunch more, are going to ship in a DirectX SDK that ships in sync with Vista Beta 2. Thank you very much.